All right, guys, in part one of our solving trig equations video, you guys learned how to solve basic trig equations. We learned how to deal with a domain of 0 to 2 pi or 0 to 360. We also learned how to adjust our answer to add in, the infinite amount of solutions we might have if we're asked for all real or all possible solutions, okay? We also gave you a couple examples that were pretty basic, and then a couple examples where factoring came into play, okay? On part two, we're going to talk about problems where using an identity, one of the identities that we've learned to help us solve a trig equation, would be beneficial to us, and also why we might need to, okay? So first things first, okay, maybe the first thing is there are some problems that might arise when we look at a trig equation. One of the problems could be that we have different trig functions. Okay. And on top of that, those trig functions might have different degrees. Okay. So if you remember back in our first video, we had a problem where we had a cosine and then a cosine tangent. Now those had different trig functions. However, we were able to factor. They all had the same degree. We were able to get everything on one side, factor out a GCF. We didn't need to use an identity for something like that, okay? However, as you might be able to see here in 3a, we have a tangent squared theta and a secant theta, okay? This has got to be fairly difficult to work with, and in fact, it might be. Okay, there is a trig identity that we have that's going to make this problem a whole lot easier to work with, okay? All right, so let's check out this one, okay? We have different trig functions of different degrees, okay? You're like, oh, this is not anything like those basic trig equations that I saw in part one, but hopefully the numerator here is screaming at you, not only is that a Pythagorean identity, but the result of using the Pythagorean identity is going to give us the same trig function as we have down in the bottom. So if you remember, 1 plus tangent squared equals secant squared. It's one of our three Pythagorean identities. So let's use it. Let's turn that into secant squared theta over secant theta equals the square root of 2. All right, fantastic. We have a squared term on top, a singular term on the bottom. We can cancel that squared and that secant. We're left with secant theta equals the square root of 2. All right, very good. We have just simplified, okay, this equation as much as we possibly could. We used an identity, made things a lot cleaner and easier for us. The reason we did that is one of our little problem areas. We had different trig functions, they had different degrees, and we used an identity to make our life easy. Turn into the same trig function, and then obviously something nice and magical happened for us where we ended up with secant theta equals the square root of 2. Okay, now, just a reminder, secant is the reciprocal of cosine, okay, and secant theta is positive in quadrants 1 and 4, same quadrants that cosine would be positive in. And then secant theta equals root 2 at 45-degree reference angles. Okay, that's because cosine would be root 2 over 2. If we do the reciprocal of that, it flips, ends up being root 2. Okay, if you want to do all that math yourself, great. If not, you can believe me that secant theta would be root 2 when cosine of theta is root 2 over 2. All right. All right, guys, so that being said, we're looking in the first and fourth quadrants at 45-degree reference angles. Let's check our domain real quick. We're looking 0 to 2 pi, so there should just be two answers here. We should be at pi over 4 and at 7 pi over 4. Easy peasy. All right. Now, the next problem area might arise if we have different angles. Different angles. Like a problem where we have a 2 theta and a theta in the same problem. Okay. Now, this might not look like they're two different angles, but they certainly are. Since we don't know what theta is, we don't know what 2 theta and theta and how they relate. Okay, but luckily for us, we learned in section 7.3 that we have identities for these double angles. So let's take a look at B. Our problem in B is that I have a 2 theta and a theta. All right. It would certainly be more ideal for us, and in fact, we couldn't actually solve this the way it's written right now. However, we do have identities for cosine of 2 theta. We actually have 3 of them. We have 2 cosine squared theta minus 1. We have 1 minus 2 sine squared theta. And we have cosine squared theta minus sine squared theta. Okay. Now, one of these is going to be, quote unquote, the right choice for us here. We can talk about why that might be. Okay, so you have 3 choices for the double angle identity for cosine. Let's look at the other side. I have a cosine theta here. Ideal situation for me is that the result of using this identity will be that there's only cosines left as well. So let's choose to use this of our double angle identities, that option. That way, we'll only have cosines left, and more importantly, we'll only have cosine thetas left. So we use our double angle identity. The right side of our equation isn't going to change at all. And again, just like we saw in our first part, this just turns into a quadratic trig equation. We have a squared cosine theta, we have a cosine theta, we have a constant. Okay, let's get everything on one side, set it equal to 0, factor solve. So I'm going to subtract 3 cosine theta from both sides. I'm going to add 2 to both sides. So I'll get 2 cosine squared theta minus 3 cosine theta. The minus 1 and the plus 2 combined to be plus 1. That's going to equal 0. Hopefully that's factorable. If it's not, we'd have to use the quadratic formula. You can always use the quadratic formula if you really would like. The only thing that multiplies to be 2 cosine squared theta would be 2 cosine theta and cosine theta. The only things that multiply to be 1 are 1 and 1. Middle term's negative, so we're going to need a minus and a minus. Let's make sure that checks out. Negative 2 cosine theta minus another cosine theta gets me my middle term. This looks great. Again, basic algebra here, the zero product property. Let's set each one of these equal to 0, and we'll solve. We get cosine theta equals 1/2. We get cosine theta equals 1. And we're looking from 0 to 2 pi. Okay, cosine is 1 at 0. Cosine is 1/2. We're looking for positive cosine values. We're looking in quadrants 1 and 4. Cosine is 1/2 at 60-degree reference angles. In radians, in quadrants 1 and 4, the angles with 60-degree reference angles, that would be pi over 3 and 5 pi over 3. Theta equals those 3 angles. All right. So that kind of solved our second type of problem that you might see, that an identity can solve that problem for us. Our problem, we had a 2 theta and a theta. Our solution was to use a double angle identity. Okay. Let's take a look here. We have different trig functions, again, of different degrees. Okay. Now, you might remember sine squared plus cosine squared equals 1. Well, remember that we can write this in different ways. That means cosine squared would equal 1 minus sine squared. Why might that be important for us? Well, if I can get this trig function to be in terms of sine squared, can you see why that would be important? Turn into a quadratic, factor solve. You guys got the hang of this. So let's use our Pythagorean identity for cosine squared. That's going to be 1 minus sine squared after I manipulate this one. All right, still have that 2 out front. Let's distribute. Again, we have a quadratic equation, we have a sine squared, we have a sine, we have a constant. Let's get everything on one side, set it equal to 0, factor solve. You guys will hear me say that quite a bit during this, this section. I'm going to move these two terms to the left so I can keep my squared term positive, or actually I could turn it positive. So we're going to add 2 sine squared to both sides. We'll subtract 2 from both sides. We get 2 sine squared theta plus sine squared theta minus 1, because I'm subtracting 2 there. Let's factor 2 sine theta, 1, 1. We want the middle term to be positive, so let's make that a plus 1 and a minus 1. Take a little shortcut here. Set these equal to 0 and solve. You'll get sine theta equals 1/2. Sine theta equals -1. Quadrants 1 and 2. This is one of our quadrantals. 1/2 at 30-degree reference angles. Just again, your unit circle knowledge here. So this should be pi over 6 and 5 pi over 6. This should be sine of theta is -1 down here, whereas 0, -1, that's at 3 pi over 2. Again, if the directions to this problem said all possible solutions, all we would do is attach it plus 2 pi k to these answers, where k is an integer. Last but not least, we have a sine 2 theta and a cosine theta. What's the issue? The issue is we have 2 different angles, a 2 theta and a theta. Luckily for us, you just learned some identities in our last section, 7.3. That double angle identity will give us the same angle. Theta's all around, so let's use it. Now we have different trig function here, but that's going to end up being okay. Here's what we can't do. We cannot divide by cosine theta. Okay, that is not what we want to do. What we want to do is move the cosine theta over, set this equal to 0. And pull out the GCF. The GCF happens to be cosine theta. What's left of the first term would be 2 sine theta. What's left of the second term would be 1. Set this equal to 0, we get cosine theta equals 0. Set this equal to 0, we get sine theta equals 1/2. Again, 30-degree reference angles, just like we did in the last one. We're going to have pi over 6 and 5 pi over 6. Cosine of theta is 0 at pi over 2. And 3 pi over 2. That's one of our quadrantals. So 4 quick examples there. We're using an identity because maybe we had different trig functions, maybe we had different angles. Helped. Pythagorean, helped. Cosine double angle, helped. We chose this one specifically because we had cosine on the other side. Pythagorean, just a manipulated version of this one, helped us because then we had sines and sines. And here, we really had no choice here. The double angle for sine is only one identity. We didn't have to choose like above. And it ended up working out for us. We ended up able to pull out a GCF and set those both equal to 0 and solve.